Year 13, Lesson 4, Sequences and Series Problem Solving. So we're going to have a look at 10 exam questions on problem solving involving sequences and series. You may wish to have a go at the question first and then use the video to check your answers. You may want to work through some questions with the video alongside you, or you may want to work through all 10 examples with the video. It is up to you. Pause as needed, but make sure you take clear notes on each question and use the PDF so that you have access to the questions as you go along. So, straight in with an interesting question. An arithmetic progression and a geometric progression have the same first and fourth terms as each other. The first term of both is a, and the fourth term of both is 12. So a1 equals 1.5 for both of them, and a4 equals 12 for both. Calculate the difference between the 10th terms of the AP and the GP. So it looks like we're going to have to find out some more information, the common difference most likely for the AP and the common ratio for the GP. So let's start with the arithmetic progression. Now we know that AK, any term, is equal to A plus K minus 1 multiplied by D. So we know that A is equal to 1.5. And we know that A4 is equal to 12. So this second piece of information here tells us that 12 is equal to A, which is 1.5, plus K minus 1, which is 3, multiplied by D. So we can use both pieces of information and this general formula here to allow us to set up a very simple equation. We can solve this to work out our value of D, which is 3.5, and then we can work out A10 using the general formula again, which is A 1.5 plus K minus 1, 9, multiplied by D, 3.5, which gives us a value of 33. Now, what about the geometric progression? This time, AK equals A multiplied by R to the K minus 1. A equals 1.5 again. A4 equals 12 again, but this time, substituting into this formula, 12 is equal to 1.5 multiplied by R to the power of 3, and we have a simple equation that we can solve. Divide both sides by 1.5, so you get 8 equals R cubed, and R then very simply equals 2. So now A10 is equal to A, which is 1.5 multiplied by R, which is 2 to the power of 9. Substitute in, and this gives. So A10 is equal to 768. Now, to finish this off, remember we needed to work out the difference between the terms. So the difference is equal to 768 subtract 33, which is equal to 735. Example 2. The second term of a geometric progression is 24. The sum to infinity of this progression is 150. Write down two equations in A and R where A is the first term and R is the common ratio. Solve your equations to find the possible values, notice, of A and R. So we have two pieces of information up here that we can deal with. I'm going to start with the information highlighted in blue first of all. So remember AK equals AR to the K minus 1. So we have been given A2, which is 24, which tells us that 24 must equal AR, and K minus 1 will just equal 1. So 24 equals AR. Now, what about this information about the sum to infinity? Sum to infinity for a convergent geometric series is A over 1 minus R. So 150 equals A over 1 minus R, and I'll rearrange this to tell me that A equals 150, 1 minus R. And we have a pair of simultaneous equations. And I'm going to substitute equation 2 into equation 1, which tells me that 24 equals, and instead of A, I'm going to write 150, 1 minus R, all multiplied by R. So just make sure you can see what I've done there. I've replaced the a here with a in terms of r. Now I'm going to end up with a quadratic equation here. Let's divide both sides by 6, which gives us 4 equals 25, 1 minus r, and let's keep simplifying. So that's 25r minus r squared. 4 equals 25r minus 25r squared. So we have this result here. Now we can factorise this, and do use your calculator to help with this if you need it. And we will find that this factorises as follows. So always do a quick double check. We go, write the 5 in there. So this gives us r equals 1/5, and this gives me r equals 4/5. Now remember, the sum to infinity exists only when r is between -1 and 1. Now in this case, we have two values of r and they both work because they're both between -1 and 1. So we can use both r values. We can use either of the equations up above to calculate a. This one gives us a equals 120, and then for the other one, a equals 30. So we have two options, either r equals 1/5 and a equals 120, or we have the option that r equals 4/5 and a equals 30. So, question 3. S is the sum to infinity of a geometric progression with first term a and common ratio r. So S, in this case, equals a over 1 minus r. Another geometric progression has first term 2a and common ratio r. Express the sum to infinity of this progression in terms of S. So this question is really testing your understanding of algebra in as much as anything else. So for the new geometric progression, its sum to infinity is equal to its first term, which is 2a, divided by 1 take away its common ratio 1 over r. We have to express this in terms of s, which is up over here. And hopefully you can see that this is two lots of a over 1 minus r, so it's very simply 2s. Part 2. A third geometric progression has first term a and common ratio r squared. Express in terms of its simplest form the sum to infinity of this progression in terms of s and r. So for this geometric progression, s infinity, remember, is its first term, a, divided by 1 minus its common ratio, which is r squared. Now we have to express this result in terms of s and r. So one way in which I might do that is to remember that that denominator there, 1 minus r squared, is a difference of two squares and can indeed be factorised as 1 minus r, 1 plus r. And then I can rewrite this as a over 1 minus r multiplied by 1 over 1 plus r. Careful there, that's a 1. And this first part here is of course equal to s. So it's s multiplied by 1 over 1 plus r, or if you like, s over 1 plus r. And I've answered the question because I've written the sum to infinity in terms of s and r. Example 4. An arithmetic progression and a geometric progression both have the same second term, which is 40. They also have the same fourth term, which is 250. Right, let's write down what we know. So we know that for the arithmetic progression, a2 equals 40, which tells me that, if you remember, for an arithmetic progression, ak is equal to a plus n minus 1d. So this tells me that 40 is equal to a plus, now n is equal to 2, so n minus 1 is 1. 40 equals a plus d. A4 is equal to 250, which again, if I use the same general formula, 250 is equal to A plus 3D, and we have a pair of simultaneous equations, and I can solve these to find the value of A. Let's call this equation 1 and equation 2. There are lots of different ways, remember, of solving simultaneous equations. I'm going to do equation 2, take away equation 1, which then gives me 210 equals 2D. So D is equal to 105, and then substitute back in to give us the value of A, which is negative 65. There we are. So part 1, done. Part 2, find the possible values of the first term of the GP. So remember, for a geometric progression, the general term is A multiplied by R to the k minus 1. So we know that A2 is equal to 40, which gives us 40 equals AR to the k minus 1. K is 2, k minus 1 is 1, so it's just 40 equals AR. A4 is equal to 250, which then gives me 250 equals A multiplied by R cubed. And I have my simultaneous equations. I'm just going to write them out in a different order. So I've got 250 equals AR cubed, and then 40 equals AR. And I'm going to divide them this time, rather than doing a subtraction or an addition, because geometric sequences are all about multiplication and division, really. So if this is equation 1 and this is equation 2, we're going to do equation 1 divided by equation 2. Now on the left-hand side, 250 divided by 40 is 6.25, and on the right-hand side, AR cubed divided by AR simply gives me R squared. I can then square root to get my value of R. Now, remember, roots can be positive or negative. My R value could be 2.5, or R could equal negative 2.5. We can then substitute back into either 1 or 2, 1 is probably a little bit simpler, to calculate the value of A, which is then 16 or negative 16. So example 5 is quite a long question. Make sure you can see this on the PDF before you get started. And let's progress. So Jill has 3 daughters and no sons. They are generation 1 of Jill's descendants. Each of her daughters has 3 daughters and no sons. Jill's 9 granddaughters are generation 2 of her descendants. Each of her granddaughters has 3 daughters and no sons. They are descendant generation 3. Jill decides to investigate what would happen if this pattern continues with each descendant having 3 daughters and no sons. So let's see if we can figure out what's going on here. So in generation 1, we've got 3 daughters. In generation 2, each of the daughters has 3 daughters, so that must mean there's 9 daughters in the next generation. And then when we're on to the next generation, where they each have 3 daughters, so we've got 27 in the next generation. So that's in generation 3. So how many of Jill's descendants would there be in generation 8 for part 1? So hopefully you can all see the clear geometric progression that we have here, where A, the first term, is 3, and R, the common ratio, is also equal to 3. Remember, AK equals A multiplied by R to the k minus 1. So we want to know how many descendants would there be in generation 8. So that would be A8, which is equal to A, which is 3 multiplied by 3 to the power of 7, which simplifies very neatly to 3 to the power 8 and is equal to 6,561. Now, the next question is interesting. Part 2. How many of Jill's descendants would there be all together in the first 15 generations? So this time we are being asked for the sum of 15 terms, so n is equal to 15. So remember, the sum to n terms is equal to a 1 minus r to the n over 1 minus r. So S15 is equal to 3, 1 minus 3 to the power of 15, all over 1 minus 3. Input that into your calculator, and this comes to a value of 21,523,359. And that's the total number of descendants. Part 3. After n generations, Jill would have over 1 million descendants altogether. Show that n satisfies this inequality. So, where is this inequality coming from? Some of you may look at this and have absolutely no idea where to start. It then asks us to hence find the least possible value of n. So we're basically finding the smallest value of n, i.e. the number of generations, after which Jill would have over 1 million descendants altogether. And the key word here is altogether, because this tells us we're looking at a sum. And what we want is the sum of all her generations, the total of all her descendants, to be over 1 million, like that. And all we're going to do is take this formula here, and we're going to input it in for Sn. Now, of course, a we know is 3. So that's 1 take away 3 to the n, all over 1 take away 3, which is negative 2, which is greater than 1 million, like so. I'm going to multiply both sides by negative 2. So I've got 3, 1 minus 3 to the n. And we're multiplying by a negative sign, so don't forget we need to reverse this inequality here. So I've got negative 2 million on the right-hand side. I'll expand this bracket on the left, so that gives me 3 minus 3 to the n plus 1 is less than negative 2 million. And then I'm going to rearrange both sides. I'm going to add 2 million to both sides. So that gives me 2 million and 3 on the left-hand side. And I'm going to add 3 to the n plus 1 onto the right-hand side, like that. Now, you can hopefully see quite clearly that in the question, the answer has been rearranged, so n is on its own on one side, and logs have been introduced. And it's very clear we've got to use log to the base 10 as well. So log to the base 10 of 2 million and 3 must be less than log to the base 10 of 3 to the power of n plus 1 on the right-hand side. Now, let's leave the left-hand side alone for the moment. So log to the base 10 of 2 million is less than n plus 1 log to the base 10 of 3. And divide both sides by log to the base 10 of 3. Now, log to the base 10 of 3 is not a negative number, so we don't need to switch the inequality sign. You may do this in fewer steps than I'm doing it. I'm just trying to make it very clear. And subtract 1 from both sides, which leaves me with n is greater than log to the base 10 of 2 million and 3 over log to the base 10 of 3, subtract 1. So let's work out what this value is on the right-hand side, and n is greater than this. So n must be greater than 12.20 ... So that gives us n equals 13 as the least possible value of n. Okay, let's take a look at the last part of the question. How many fewer descendants would Jill have altogether in 15 generations if instead of having 3 daughters, she and each subsequent generation has 2 daughters? So we are looking at a slightly different geometric progression where a is equal to 2 and r is equal to 2 as well. N is equal to 15. So the sum of 15 terms we can work out using our formula. And this comes to a value of 65,534. Now we need to subtract that from the previous value, which was 21,523,359. and this leaves us with an answer of 21,457,825. Example 6. A geometric progression has first term a in common ratio r, the second term is 6, and the sum to infinity is 25. So we've now got to write down two equations in a and r, so that will be done using this information from up above. So starting with the first piece of information, we know the second term is 6. So remember that ak is equal to a multiplied by r to the k minus 1. So we know that a2 is equal to 6, so that tells us that 6 is equal to a multiplied by r, and k minus 1 is just 1, because of course k is equal to 2. So there's one equation. We know the sum to infinity is 25. Remember, the formula for the sum to infinity is a over 1 minus r, so this tells us that 25 is equal to a over 1 minus r. And we have a pair of simultaneous equations. We need to solve these and show that one possible value of a is 10 and find the other possible value, and then write down the corresponding values of r. So let's solve these simultaneous equations. So equation 1, equation 2. I am going to rearrange equation 2, so it tells me that a is equal to 25 or 1 minus r, and we'll substitute that into equation 1, which then tells me that 6 is equal to 25, 1 minus r multiplied by r. We've been here before. This is a quadratic equation. So 6 is equal to 25r, take away 25r squared. 25r squared minus 25r plus 6 equals 0. And then I can factorise this. So make sure you don't just copy this down, have a go at factorising this yourself. Use your calculator as well. Remember, there's the quadratic solver on your calculator, which could be useful too. So this then gives me r equals 2/5 or r equals 3/5. Now we can substitute back into equation 1 to work out our values of a. So if r equals 2/5, a is then equal to 15. And then if r is equal to 3/5, a is equal to 10, which is what we were required to show. So part 2, show that the ratio of the nth terms of the two geometric progressions found in part 1, that's these two, can be written in this format over here. So let's get started with this. So we need to find the nth terms of these two separate geometric progressions. So an is equal to ar to the n minus 1 for the nth term. So for the first one, an is equal to 15 multiplied by 2/5 to the power of n minus 1. And for the second result, an is equal to 10 multiplied by 3/5 to the power of n minus 1. Now the ratio of these is going to be 15 2/5 to the n minus 1 to 10 3/5 to the n minus 1. And what we have to do is now simplify this and show that we get this result at the end. So here's what I am going to do. I'm going to write each part out a little bit differently. So I've got 15 multiplied by 2 to the n minus 1 all over 5 to the n minus 1 in a ratio with 10 multiplied by 3 to the n minus 1 over 5 to the n minus 1. Now remember, we can multiply or divide across both parts of a ratio and the result will still be equivalent. So imagine we multiply both sides of this ratio by 5 to the n minus 1, so we lose the denominators. So we've got 15 multiplied by 2 to the n minus 1 in a ratio with 10 multiplied by 3 to the n minus 1. Now 15 and 10 both have a common factor of 5, so it makes sense to divide across by 5. So this gives me 3 multiplied by 2 to the n minus 1 in a ratio with 2 multiplied by 3 to the n minus 1. Now, here's what I'm going to do next. I'm going to divide both sides of this result by 3. So on the left-hand side, the 3 vanishes, disappears, it cancels out, and I'm left with 2 to the n minus 1 in a ratio with 2 multiplied by. Now remember, I'm dividing both sides by 3, so 3 to the n minus 1 divided by 3. Think about what happens when you carry out a division and the bases are the same. You subtract your indices. So 3 to the n minus 1 divided by 3 to the 1 is 3 to the n minus 2. So I end up with 3 to the n minus 2. I'm going to do something very similar to both sides. I'm now going to divide them both by 2. So on this side, we're dividing by 2. So again, you've got 2 to the n minus 1 divided by 2 to the 1. Subtract your indices, so you're left with 2 to the n minus 2. And on the right-hand side, the 2 disappears, so you're left with 3 to the n minus 2. And here is your ratio, as required. There's quite a lot of interesting algebra in this part here. Do go back through this carefully and make sure you understand all the steps. Don't just copy it all down and assume that you would be able to do a similar question later on. You must make sure you've understood every piece of the algebra here. So example 7, there's a lot of text here. Make sure you've read through the question really carefully using the PDF. We're going to start part 1 on the next page. So Jim and Mary are each planning monthly repayments for money they want to borrow. Jim's first payment is £500 and he plans to pay £10 less each month, so his second payment is £490 and his third is £480 and so on. So hopefully you can see that this is an arithmetic progression, starting off with 500, then 490, then 480 and so on. So for part A, we've got to calculate his 12th payment. Well, let's identify the features of this arithmetic progression. A is 500 and D, the common difference, is equal to negative 10. Now we're calculating the 12th payment, not the total of the payments, so it's important that we recognise we're working out what A12, the 12th term, is. Keep going back to your formula for the general term. AK equals A plus K minus 1 multiplied by D, so A12 is equal to 500 plus 11 multiplied by negative 10, which gives you an answer of £390. Part B. He plans to make 24 payments in total, or altogether. Show that he pays £9,240 in total. So we're looking at the sum of 24 terms here. Let's remind ourselves that for an arithmetic progression, Sn equals a half n, 2a plus n minus 1 multiplied by d, and of course n equals 24. So that is a half n, which is 12, multiplied by 2a, 1000, plus n minus 1, 23, multiplied by d, negative 10. So that is 12, multiplied by 1000, take away 230, and simplifying this, you will find that you get 9,240 in total. So let's read about Mary's payment plan. Her first payment is £460 and she plans to pay 2% less each month. So that's really simple. If A1 equals 460, A2 would equal 460 and you're paying 2% less, so there's a multiplier here of 0.98. Thinking about your percentage multipliers, which means that the second payment is £450.80. So this is very clearly a geometric progression where the first term A is 460 and the common ratio is 0.98 because you pay 2% less than the previous amount each time. So for part A, calculate her 12th payment. So you want to use AK equals AR to the K minus 1. And A12 is then equal to 460 multiplied by 0.98 to the power of 11, which equals 368.336 ... We will round that to £368.34 to the nearest penny. Part B. Show that Jim's 20th payment is less than Mary's 20th payment, but that his 19th payment is not less than her 19th payment. So we've got quite a lot of calculation to do here. So let's start with Jim. So we want to work out Jim's 19th payment and we want to work out Jim's 20th payment. So we're going to have to go back to our arithmetic progression for Jim. So A19 is 500 plus 18 multiplied by negative 10, and A20 is 500 plus 19 multiplied by negative 10. So let's work out both of these, and they come to 320 and 310 pounds, respectively. Now, let's do the same for Mary. So her value of A19 is going to be 460 multiplied by 0.98 to the power of 18, which comes to a value of 319.7622 ... And her 20th payment is 460 multiplied by 0.98 to the power of 19, or you can just take A19 and multiply it by 0.98. And this is 313.3670 ... So we've demonstrated everything we need to here. Jim's 20th payment is less than Mary's 20th payment, but his 19th payment is not less than her 19th payment. Right, part C. Mary plans to make 24 payments altogether. How much does she pay in total? So for part C, n is equal to 24. So let's work out how much she pays in total. S24, we're working out a summation. So remember, Sn, a 1 minus r to the n over 1 minus r for a geometric progression. So a was equal to 460, r is 0.98, and input this into your calculator to see what you get. And this comes to £8,837, which will round £8,837 and 5 pence to the nearest penny. Part D. How much would Mary's first payment need to be if she wishes to pay 2% less each month as she has done before, but to pay the same in total as Jim, £9,240 over the 24 months? So let's set the total of her payments, S24, equal to 9,240. But we're going to have to use this formula because, of course, she's working with a geometric progression. Now, we are still using r equals 0.98 because she wishes to pay 2% less as before each month, but our a value is unknown. So when we substitute in, a will remain as a. And let's input in all of the other information. This equals 9,240, and then simply work out the value of a from here, and a then equals 480.974 ... So that means her first payment has got to be £480.97 to the nearest penny. Right, example 8. Make sure you have access to this question. We're going to move on to the next page before we start working it out. So, an arithmetic progression has first term A and common difference D. The sum of its first two terms is 25 and the sum of its first four terms is 250. Find the values of A and D. So, part 1, part A. Let's think about what we have here. So we know that the sum of n terms of an arithmetic progression is equal to half n 2a plus n minus 1 multiplied by d. Now we're told the sum of the first two terms is 25. So that's S2, the sum of the first two terms. So 25 must equal a half multiplied by n, well n is 2, so that's 1, 2a plus n minus 1, well n is 2 again, so n take away 1 is just 1, plus d. So we have our first equation here. Now let's look at the sum of the first four terms, S4. So this time n equals 4. Substituting that into the sum to n terms formula, 250 equals a half n, so that's 2 lots of 2a plus n minus 1, which is 3 multiplied by the common difference. So we have a very, very simple pair of simultaneous equations. I think what we'll do is we'll just simplify this second one a little bit. So divide by 2, so that gives me 125 equals 2a plus 3d. We'll call that equation 1. And then equation 2 we'll write underneath, 25 equals 2a plus d. And then we can carry out a simple subtraction. Equation 1, take away equation 2, 100 equals 2d, so d is equal to 50, and substitute that to work out your value of a, which is negative 12.5. And we can use these results in part B of the question, which is to find the sum of the 21st to 50th terms inclusive of this sequence. Now, if we work out what S50 is, we get the sum of the first 50 terms. So let's do that. So that would be a half multiplied by 50, multiplied by 2 lots of a, which is negative 25, plus 49 multiplied by d, which is 50. So this gives me a value of 60,625. Now, I want to work out the sum of the 21st to the 50th terms inclusive. So I want to get rid of the total of the 1st to the 20th term, which will leave me with the sum of the 21st to the 50th terms. So I'm going to work out S20. So it's a half multiplied by 20, 2 lots of a is negative 25 plus 19, which is n minus 1, multiplied by d, 50. So this gives me 9,250. So the answer to my question is going to be the value of S50 subtract S20, which comes to 51,375. Part 2. We are moving swiftly on to a geometric progression with the first term a and common ratio r. The sum of the first 2 terms is 25 and the sum of the first 4 terms is 250. Now, use the formula for the sum of a geometric progression to show that we get this result here, and hence or otherwise find algebraically the possible values of r and the corresponding values of a. There is a lot to do in this question. Let's start with the information that we were given here. The sum of the first 2 terms is 25 and the sum of the first 4 terms is 250. So you should all remember, for a geometric progression, the sum of n terms is given by this formula over here, and we're going to be making use of this formula. So let's start off with sum of the first 2 terms. So that's 25, which is equal to a, 1 minus r to the power of n, which is 1 minus r squared, over 1 minus r. We then know that S4 is equal to 250, so that is equal to a 1 minus r to the 4 over 1 minus r, and we have to take these 2 results and show that they give us this piece of information. Now it's clear this piece of information does not include a, so let's eliminate a. I'm going to rearrange both results so they are in the format a equals. It's a very easy bit of algebra here in both parts. Make sure you can follow this carefully. And both results are, of course, equivalent to a, which means we can equate both results. So this then tells me 25, 1 minus r over 1 minus r squared equals 250, 1 minus r over 1 minus r to the power of 4. Now, r is not equal to 0, otherwise you wouldn't have any sort of sequence at all. So let's cancel out 1, take away r on both sides, and we can also divide by 25. So we're left with 1 over 1 minus r squared equals 10 over 1 minus r to the power of 4. Now, a tiny bit of rearrangement here. and we'll get 1 minus r to the power of 4 over 1 minus r squared equals 10. Now that's not quite what we have in this result over here, so we simply need to multiply the numerator and the denominator of our result by -1, which gives us r to the 4 minus 1 over r squared minus 1 equals 10 as required. Now, the last part of this requires us to find the possible values of r and the corresponding values of a. So there are lots of interesting ways in which you might solve a problem like this. Those of you thinking about this very carefully may realise that r to the 4 minus 1 is a difference of two squares, and it can be factorised as r squared minus 1, r squared plus 1. The denominator remains r squared minus 1, and this is equal to 10. Now, we can cancel through by r squared minus 1 because earlier on in the question we were told that r is not equal to plus or minus 1, which means r squared is not equal to 1. So this then gives us r squared plus 1 equals 10, r squared equals 9, r equals plus or minus 3. So if r equals 3, we can calculate the corresponding value of a, and if r equals -3, we can calculate the corresponding value of a. We can use one of the equations we had previously. For instance, 25 equals a 1 minus r squared over 1 minus r, which we had rearranged to tell us that a equals 25, 1 minus r over 1 minus r squared. So substitute these values of r in and let's work out a. So if r equals 3, a equals 6.25, and if r equals -3, a equals -12.5. Make sure you're working these answers out yourself and not just copying them down. Example 9, again, another long question, so make sure you can see this very clearly on the PDF before you start working through it. Okay, so a firm takes on 2 new employees. Arif starts on an annual salary of £30,000 and his salary increases by £1,000 each year after that. So hopefully straight away you can see that Arif is working with an arithmetic progression salary. First term A, £30,000, and common difference D, £1,000 after that. Now, Bettina starts on an annual salary of £25,000 and her salary then increases by 5% each year after that. So that straight away tells us that Bettina is working on a geometric progression salary. Her first term is £25,000 and her common ratio is an increase of 5%, which means the common ratio is 1.05 as a percentage multiplier. So part 1, show that Arif earns more than Bettina in year 10 of their employment. So we're not looking at their total salary over 10 years, we're looking at the salary in year 10 and then in year 11. So let's look at each of these years separately, and remember that for an arithmetic progression, a general term is AK, which is A plus K minus 1D, and for a geometric progression, AK is equal to A multiplied by R to the K minus 1, using these formulae correctly. So let's start with year 10 of their employment. So Arif will have A, which is 30,000 plus 9 multiplied by 1,000. So that gives his value of A10 equal to £39,000. Now Bettina, her value of A10 is going to equal 25,000 multiplied by 1.05 to the power of 9, which comes to 38,783.205 ... which is clearly less than 39,000. So what happens in the second year, year 11? So for Arif, A11 will simply equal £1,000 more than A10, so that's £40,000. And again, for Bettina, we can work out A11 very simply by taking her value for A10 and multiplying it by an increase of 5%, so 1.05. And this gives her a value of £40,722 365, which is clearly greater than Arif's salary of £40,000. Now, part 2. Show that the total amounts earned by each of Arif and Bettina during their employment up to the end of year 17, correct to the nearest £100, are equal. So we're looking at total amounts here. Now, for an arithmetic progression, the total sum of n terms is equal to a half n to a plus n minus 1d. And for a geometric progression, remember, Sn is given by this formula. So we need to make sure we're using the right formula in the right example. So for Arif, let's work out his total salary up to the end of 17 years. So that's a half multiplied by 17, 2 lots of A's, 2 lots of 30,000 plus n minus 1, which is 18, multiplied by d, which is 1,000. So this gives his salary after 17 years to be £646,000. Now for Bettina, S17 is equal to 25,000 multiplied by 1 take away 1.05 to the 17, all divided by 1 take away 1.05. Input that into your calculator and you find you get 646,000 and 0.15 ... So if we round this to the nearest whole pound, that's also 646,000. So we can see that the amounts are equal. Let's say to 6 sig figs. Part 3. At the end of year n, the total that Bettina has earned during this employment is greater than m. Show that we get this result over here. So we've been here before. This is one of those questions where we've got to show that the total can be written in this logarithmic format. So let's do that. So we know that Sn equals a 1 minus r to the n over 1 minus r. We're going to use this formula up over here. So we're also told that Sn is greater than m pounds. So here's what I'm going to do. I'm going to say that A, £25,000, 1 minus 1.05 to the power of n over 1 minus 1.05 must be greater than m. Now let's simplify this a little bit. So that's 25,000, 1 minus 1.05 to the power n. And I'm going to multiply by this denominator. Now the denominator is 1 minus 1.05, which is negative 0.05. So when I multiply by that, I must switch the inequality sign round and reverse it like that. So I then get negative 0.05m on the right-hand side. So a bit of rearranging. We've got 25,000 minus 25,000 multiplied by 1.05 to the power n is less than negative 0.05m. So I'm going to add 0.05m to both sides, and I'm going to add the 25,000 times 1.05 to the n as well. So I just do a little bit of rearranging. Watch what happens. So I've got 25,000 plus 0.05m, and that is less than 25,000 multiplied by 1.05 to the power of n. So what am I going to do next? Now, at this point, it's worthwhile looking at the answer that you are trying to get to here, because if you don't know what that looks like, you may end up not really focused on how to get there very easily. So I can see in the bracket here, there's just an m rather than 0.05m. So I'm going to factorise on the left-hand side. I'm going to take 0.05 out of a bracket, which leaves me with 500,000 plus m, which is what we are expected to get to in the answer. On this side over here, we've still got this. Now, I'm now going to divide both sides by 0.05. So on the left-hand side, I've got 500,000 plus m, and on the right-hand side, I've got 500,000 multiplied by 1.05 to the power n. So now let's take logs of both sides. We're going to take log to the base 10. So log to the base 10, 500,000 plus m, is less than log to the base 10 of 500,000 multiplied by 1.05 to the n. Now, we can split up the logarithm on the right-hand side using the log rule that log of pq is equal to log of p plus log of q. So splitting up the product. So on the left-hand side, we still have log of 500,000 plus m. On the right-hand side, we have log of 500,000 plus log of 1.05 to the power n. And we're then going to use another log rule, which will allow us to bring this n down to here. And at this point, you should be able to see how we're getting to the final answer. So here we go. Let's keep simplifying. So log 500,000 plus m, subtract log 500,000 is less than n log 1.0. So simply dividing by the log of 1.05 then gives us the result that we were required to get to. Now, the end of this question simply makes use of this, hence find the year in which year the total earned is first greater than £1.2 million. So we need to substitute m equals £1.2 million into this result here, and this gives us n is greater than 25.082 ... So n equals 26 years for the first year during which she earns more than a total of 1.2 million. Right, example 10, the last question. Again, a long question. Make sure you read it all through very carefully from the PDF before we get started. So, Andre is playing a game where he makes piles of counters. He puts 3 counters in the first pile. Each successive pile he makes has 2 more counters than the previous one. So, A1 is equal to 3, A2 is equal to 5, A3 is equal to 7. So hopefully we can all see very clearly this is an arithmetic progression. First term A, common difference equals to 2. So how many counters are there in his 6th pile? A6 is equal to, so remember we're going to use AK equals A plus K minus 1D as the formula for any term in an arithmetic sequence. So that is 3 plus 5 multiplied by 2, the common difference, so that is 13 counters. Part 2. He makes 10 piles of counters. How many counters has he used altogether? So key word here, altogether. This tells us that we're working out S, the sum of 10 piles. So we want to know Sn, so we're going to use a half n 2a plus n minus 1d, sum of n terms of an arithmetic progression. So that is a half multiplied by 10, 2a, which is 6, plus 9 multiplied by 2, and this comes to a value of 120. Part B. In another game, played with an ordinary fair die and counters, Betty needs to throw a 6 to start. The probability, Pn, of Betty starting on her nth throw is given by this result here. Calculate P4. So that's 1/6 multiplied by 5/6 to the power of 3. And we need to give our answer as a fraction. So this is 125 over 1,296. So, part 2. The values P1, P2, P3 form an infinite geometric progression. State the first term and the common ratio of this progression. So there's a lot in this question. Make sure you've read it very carefully. We're on this part here that I've highlighted in red. So the first term will of course be P1, which is equal to 1/6 multiplied by 5/6 to the power of 0, which is just 1/6. Now, the common ratio you can hopefully see from the format is 5/6 because you're clearly multiplying by 5/6 each time. And this result here has the same format as AK equals A multiplied by R to the n minus 1. So we can hopefully see that the common ratio is 5/6. Now, hence show that the sum of infinite terms is equal to 1. So S infinity. Now remember the formula for this, S infinity equals A over 1 minus R. S infinity only exists, the sum to infinity only exists if the geometric progression converges, i.e. if R is between 1 and minus 1, which it is. So let's substitute in, so that's 1/6 divided by 1 take away 5/6, which we can see very clearly comes to an answer of 1. Now, given that Pn is less than this number, show that n satisfies this inequality here. And then we've got one last part highlighted in red. So let's start this off. Pn is less than 0.001. Now we have a formula for Pn in a blue box up over there. So we know that 1/6 multiplied by 5/6 to the power of n minus 1 is less than 0.001. Multiply both sides by 6, so 5/6 to the power of n minus 1 is less than 0.006. Let's take logs of both sides. So log to the base 10 of 5/6 to the n minus 1 is less than log to the base 10 of 0.006. Let's pull n minus 1 to the front down like that. So n minus 1 log to the base 10, 5/6 is less than log to the base 10, 0.006. And we can see it's a very quick process now to then finish off the rest of the algebra here. And then it's a very quick process to the end of the work here. So we can see that n log to the base 10 of 5/6 is less than log to the base 10 of 0.006 plus log to the base 10 of 5/6, expanding the blue bracket and adding log to the base 10 of 5/6 to both sides. We then simply divide by log base 10 of 5/6, but this is less than 1, which means that the inequality sign will have to reverse. We'll finish off the answer up over here. So that tells us that n is greater than log to the base 10 of 0.006 over log to the base 10 of 5/6. And of course, if you divide log to the base 10, 5/6 by itself, you have your plus 1 there. Now, the last part of this question asks us to find the least value of n for which Pn is less than 0.001. So we simply need to evaluate the result on the right-hand side, which gives us n is greater than 29.060 ... So the least value of n is, of course, then 30, because n has got to be greater than 29.06.